Okay, so in this video, we're going to be talking about Laplace transform properties, very similar to how we had Fourier transform properties, okay? And a lot of these properties can be proved in a very similar method as to how we prove the corresponding Fourier transform properties. And so I'm not going to be proving them in this video. This video is mostly so that you're just aware these properties exist. Okay, and some of them actually we probably don't have all of the tools we need to prove them rigorously, but that's okay because a lot of them we could, and you can try that on your own. And the other ones, it's just good to be aware of. And the other part of these properties is that for each property, you have to also kind of think about how the region of convergence would change. Let's say you differentiate. How does the region of convergence of the Laplace transform change? But again, for the purposes of this video and this class, we're going to mostly focus just on the actual Laplace transform properties and the region of convergence, how that changes for each of these properties. I can leave to you to think about on your own, or you can look up. You'll probably see it in a future class at some point, but we're not going to really cover it here. Okay, so the first property is linearity. Okay, we know the deal with this. We've seen this many times. So if A and B are complex numbers, and I have these two Laplace transform pairs, okay, and x2 of t has Laplace transform x2 of s, okay, then I bet you can guess. So a times x1 plus b times x2 is going to have Laplace transform the same linear combination of the corresponding Laplace transforms. Okay, so that's linearity, and this is the property for Laplace transforms proved in exactly the same way as Fourier transforms. Okay, and I'll just do an example of how the ROC changes here, but I'm not going to do this on the future ones. Okay, but if this has ROC R1 and this has ROC R2, it turns out that the best you can do, I'll just put it in parentheses, the most you can say about the resulting ROC, I'll call it R, is that it contains the intersection. Okay, it contains the intersection of R1 and R2. Okay, so as we go through and do more things in this class, sometimes we'll be able to obtain the ROC from, say, a sum of two Laplace transforms by looking at it in that specific case, which we can do. But in general, the most you can say is that the ROC, the new ROC of this linear combination just contains the intersection of the other two. Again, we're not going to focus on how the ROC changes with these properties in this class. We're just going to focus on the actual properties themselves about the Laplace transform. And maybe in a future class, you will deal more with how the ROCs change. Okay, well, let's see an example of this. So x of t, let's say it's e to the negative t u of t minus e to the t u of negative t. Okay, what does that look like? Well, when t is positive, I have this decaying exponential. When t is negative, I have, without this negative sign, it would be increasing like that. Well, it's still increasing, it's just negative, so it looks like that. Okay, so this is my x of t. All right, so let's take the Laplace transform. Okay, so this is a linear combination of two functions that we know the Laplace transforms of. Okay, so we know the Laplace transform of e to the negative t u of t, and we know the Laplace transform of negative e to the t u of negative t. Okay, we know both of these. We covered them in a previous video. Okay, and what were they? Well, the Laplace transform of this function we saw was 1 over s plus whatever is stuck right in there. So that the general property, the general form of this function was either negative at u of t. So a here is 1, and we get 1 over s plus 1. Okay, plus, if you look back in your notes, you'll see the Laplace transform pair of this function was 1 over, okay, and again, it was e to the negative at, at least that part. It was negative e to the negative at u of negative t. And the Laplace transform pair with this was, again, 1 over s plus a. It's just here now, a has to be negative 1 because we have e to the t. This is s plus negative 1, which is just s minus 1. Okay, so that's just using Laplace transform pairs we've seen before. And we can also look at the ROC. The ROC here, this is our right-sided function. And so it was when the real part of s was greater than that pole, s equals negative 1. Okay, and here, this was our left-sided function, anti-causal, So this is when the real part of S was less than the pole here, which is 1. Okay, and you can look back in your notes. Okay, we went over these properties. I'm just using that information. Okay, and so in order to get the Laplace transform to converge here, okay, in order to get this Laplace transform to converge, we need both of these to converge. In other words, we need our S value, okay, to satisfy this and this. We need both of them to be satisfied. And so if we plot what the region of convergence would be in this case, okay, we need both of these, we need S to satisfy both of these properties. Okay, so we need the real part of S to be greater than -1. Okay, that was a pole. And also less than 1. That was another pole we had. Okay, so that means it's actually in between here. And this shows us that this is our ROC. And the reason that our ROC is this vertical strip and not, something going all the way to the right to infinity or to the left is because our function here isn't just right-sided or left-sided. It's actually two-sided. Our function x of t is two-sided. It has non-zero values going both directions. And so that turns out to be why we get this middle strip here for our ROC. Okay, and so this is a case where this property is true. The new ROC contains the intersection, actually happens to equal the intersection. And so in particular cases like this, we can go through the logic and still find the ROC when we have a function that is some linear combination of other functions that we know the Laplace transform of. It just turns out this is all you can say in general. Okay, but anyway, so that's an example of using linearity. All right, so the rest of the properties, I'm not going to worry about the ROC. I'm just going to write down the Laplace transform properties so that you're aware of them and can use them. And we're going to be using these very similarly to how we use the Fourier transform properties, and you'll see they're very similar in form. Okay, so if x of t has Laplace transform x of s, then what happens when I shift in time? Well, I get x of s times e to the negative s t naught. Okay, remember for the Fourier transform, we just had j omega right there instead of s. And remember, that was how we got the Fourier transform from the Laplace transform. You just plug in a 0 for the real part and j omega for the rest of the s values so that you're on this imaginary axis, and there's the Fourier transform, right? That was how Fourier was a special case of Laplace. You can see here, just plugging j omega in for s, we get the corresponding Fourier transform property. Okay, how about a shift in the s domain? So if I have this Laplace transform pair, then what happens when I look at x of s minus s naught? Well, as you might remember, we get a e to the, in Fourier, it was j omega t, okay? Or it was j omega naught t, sorry, because we're shifting by omega naught now, but now we're shifting by s naught, so we're just going to get s naught t. Okay? And you can, like I'm kind of hinting at, you can match these up with the Fourier transform properties to see the comparison. Okay, how about time scaling? Okay, so if x of t has Laplace transform x of s, then what happens when I scale my time function? Well, again, should remind you of the Fourier transform property. This is what we get. Okay, so we get 1 over the absolute value of a out front, and then the s argument is scaled in the opposite way as the time argument scaled. So t gets multiplied by a, s gets divided by a. And that's sort of hinting at that inverse relationship between sort of time and frequency in the Fourier transform. And here we have time in the s domain. All right, what happens when we take a derivative in time? Okay, if I have this Laplace transform pair, then when I take a derivative, I get an extra factor of s. Okay, if you remember for Fourier, we got an extra factor of j omega right there. How about a derivative in the s domain? Okay, well, if I have this Laplace transform pair again, Then what happens? Well, when I differentiate in S, in time, I end up multiplying by -t. Okay, and by the way, of course, if I had this property, if I took another derivative in time, I would just get another factor of S here, right? If I took another derivative in frequency, I would just get another factor of -t. So you can apply these properties, of course, multiple times. Just thought I'd point that out. Just a couple more here. So what happens when I conjugate? So conjugation. Okay. So if x of t has Laplace transform x of s, then x conjugate of t, what happens? Well, I get x conjugate of s conjugate. Okay, and if you remember in Fourier, we got x conjugate of just negative omega, right? Because in that case, if you take just j omega and conjugate it, you just get negative j omega. Okay, so when the argument to the Laplace transform is purely imaginary, it does just get negated. That was the situation with Fourier. But here for Laplace, we have a more general argument of S that could have a real part, so we have to write S conjugate. Finally, last one, convolution. Okay, so now if I have x1 of t, and it has Laplace transform x1 of s, and I have x2 of t, and it has Laplace transform x2 of s, then what happens when I conjugate? Well, I bet you all can guess. Conjugation in time is multiplication in the S domain, just like for Fourier. Okay, so of course there are more properties I'm not mentioning here, but this is a good amount of properties to get you started. Okay, and they're used just in the same way as Fourier properties, so it should feel pretty natural. And again, there are differences in how the region of convergence changes. You can try and think about that on your own or look it up. It is interesting, and you'll likely see it in a future class. But for this class, we're just going to stick to the properties as they pertain just to the Laplace transforms themselves. Okay, so that's all I had for this video, and I'll see you in the next one.